The following
I'll just mute my microphone.
Content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Today, we begin with the harmonic oscillator. And before getting to the harmonic oscillator, I want to touch on a few concepts that have been mentioned in class and just elaborate on them. It is the issue of nodes and how solutions look at and why solutions have more and more nodes, why the ground state has no nodes, this kind of stuff. So these are just a collection of remarks and an argument for you to understand a little more intuitively why these properties hold. So one first thing I want to mention is if you have a Schrödinger equation for an energy eigenstate, Schrödinger equation for an energy eigenstate, you have an equation of the form minus h squared over 2m d second dx squared psi of x plus v of x psi of x equal e times psi of x. Now, the issue with this equation is that you're trying to solve for two things at the same time. If you're looking at what we call bound states, now what is a bound state? A bound state is something that is not extended all that much. So a bound state will be a wave function that goes to 0 as the absolute value of x goes to infinity. So it's a probability function that certainly doesn't extend all the way to infinity. It just collapses. It's normalizable. So these are bound states. And you're looking for bound states of this equation. And your difficulty is that you don't know psi and you don't know e either. So you have to solve a problem in which if you were thinking, oh, this is just a plain differential equation, give me the value of E. We know the potential, just calculate it. That's not the way it works in quantum mechanics because you need to have normalizable solutions. So at the end of the day, as will be very clear today, this E gets fixed. You cannot get arbitrary values of E's. So I want to make a couple of remarks about this equation, is that there's this thing that can't happen. If V of x, certainly if V of x is a smooth potential,
at Stanford University.
Classical mechanics is basically a set of rules about what those laws of motion look like. It's a set of rules, and in fact, there are two varieties of questions. The first question is, I'm not sure about the order of them, but let's take them first. The first kind of question is, what are the specific laws for particular kinds of system? Particular system could be a planet moving in the field of a heavy mass. That has its own particular laws. Those laws are different than an electrically charged particle moving in the field of a magnet. They're different than, there are specific laws of nature. Okay. Then there's a more general framework. What are the rules for the allowable laws? Are there rules for the allowable laws? What's the grand framework in which all of the various different specific laws are framed in? And it's really the second question which we're really interested in. The first question will provide us with illustrations of the principles that govern what the allowable laws of physics are. Okay, so I like to start, and I always do in these classes, with a very simple set of illustrations. Who can guess what my illustrations are going to be? Coins, right? Right, of course. That's because you've been here before. Coins. Let's take the very simplest system that I can think of, a coin. I don't have a coin. So, when I say a coin, I mean an abstract coin laid down on an abstract table. The only thing about the coin which is relevant to us is whether it's heads or tails. The coin has two states of being, two configurations, two values, however we want to call it, heads or tails. Right? So there are two states. This is our dynamical system. It's one coin, and it has two states, heads or tails. That's all there is to the world, to this very simplified world. Question? Of course, there's an even simpler world. We can even go back to a simpler world. It's a coin with only one side. Then it's even simpler. All it can be is that one state. Right? That's a little too simple. Nothing can happen. Nothing ever happens. So this is our world. What is an initial condition? An initial condition is it's either heads or tails. Now, what about laws of motion? Now we're going to make up some laws of motion. The laws of motion, of course, for this coin that just sits here, the law of motion is very, very simple. Let's put two circles here. One stands for heads and one stands for tails. What is the law of motion of this particular coin sitting on this particular table? The answer is it stays the same. So if we imagine breaking up time into little successive intervals, this stroboscopic world of a discrete coin like that, then the only thing that happens is nothing happens. Heads goes to heads, tails goes to tails. Or we can draw a picture. Heads goes to heads. Starting with heads, we go back to heads. Tails goes to tails. That's really a very boring law of physics, but it's a very powerful law of physics in that it tells you, however you start, you know where you will be arbitrarily down the line in time, right? If you start with heads, the history of the world will be heads, 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 dot, 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 forever and ever. So this law may be very boring, but it's very powerful. Or if you start with tails, it's going to be tails, 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 as far as the eye can see. So that's an example of a dynamical system with a law of motion, where the law of motion is just an updating, but it's in this case very trivial. There's only really one other law of motion that you can imagine for this system. And what is it? It is that whatever it is at one instant, at the next instant of the stroboscopic light, it's the opposite. In the next instance, it's the opposite. We could write it this way. Heads goes to tails, tails goes to heads. And we can make a picture of it. We could picture this law of motion by, again, arrows. An arrow from head to tails, which says that if you start at heads, the tail end of the arrow always means what you start with. The head end of the arrow means where you'll end up. And that would be this law of physics. Heads goes to tails goes to heads goes to tails. And the history now of the world would be, if you start with heads, you then go to tails. Then you go to heads, then you go to tails, dot, dot, dot. But if you start with tails, you go to heads, tails, heads. Still pretty boring, but a little more interesting than the original first law. We could write some mathematics for this. In fact, we can write an equation of motion. Let's invent a symbol, a variable, which takes two values. Let me call it sigma. Why do I call it sigma? It's because sigma is a traditional variable associated with two-valuedness in physics. It has to do with the spin of the electron, or spin of particles, but we don't need to know about that now. Sigma is a variable that is either equal to 1, let's say, or minus 1. 1 for heads, minus 1 for tails. All right, so we can, instead of calling this heads and tails, we can call it sigma equals 1 and sigma equals minus 1. All right, we now have the idea of a configuration space which is labeled by the two possible values of a certain variable. It's not as rich as the variables we will use, for example, positions of particles, values of fields, or all sorts of other things. But nevertheless, it's a mathematical symbol whose value tells you which of the configurations you're in. All right, let's take this first law of physics. The first law of physics, not the first law of physics, the first law that I wrote down, the previous law, that was heads goes to heads and tails goes to tails. Let me write that in a mathematical form. Oh, let's call time t, and in our stroboscopic world, t is an integer. T is 0, 1, 2, 3. It can also be minus 1, minus 2, minus 3. So in the stroboscopic world, time is discrete, and it takes on integer values. So let's see if we can write an equation for the most boring law in the world. What it says is that whatever sigma is at a given time, let's put that over here, sigma at time t, at the next instant, t plus 1, it will be equal to whatever it was at the instant t. This is just a law that says that the spin, or that the coin doesn't flip. It just stays the same. Whatever it is at one time, it will be the same at the neighboring time, at the next time. Okay? So that's the simple law, heads, 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 or tails, 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 tails. What about the other law? The one which says that the coin does flip between each successive flash of the stroboscope. That's easy. That just says sigma of t plus 1 is equal to minus sigma of t. If it starts at 1, then at the next instant it's minus 1. If it starts at 1, at the next instant it's the opposite. So there we've written down equations of motion for a very, very simple system. Notice that it is completely predictive, completely deterministic. There's no ambiguity about what happens arbitrarily far down the future. Now, of course, I could come in and grab the coin and do something with it and do something else with it. That would disturb it. In our language that we've set up now, that would be because the system was not closed. I intervened, and I was not part of the system. So for a closed system, laws of physics are completely deterministic in classical mechanics. Okay, now let's think about a more complicated system. more complicated system, not much more complicated, instead of a coin, let's take, what's the next case, friends? A die, half of a pair of dice. You know, I never knew until I started teaching this that the singular of dice was die. I really didn't. Somebody corrected me once. I guess I called it a dice. And somebody said, do you mean a die? And I guess I did. Okay, so we have a die. A die has 6 states. 1, 2, 3, 4, 5, 6. That's the only significance for our purposes today about the fact that it's a die, is that it has 6 states. Again, we could label the 6 states 1 through 6. Let's put them 1, 2, 3, 4, 5, 6. And these stand for the 6 different configurations of laying the die down on the table. Okay. That's an initial condition. An initial condition is a choice of one of these 6 configurations. Right? But what about a law of physics? What about a law of motion? An equation, not an equation. I'm not going to write an equation. It's a little bit too complicated. But what's a possible law of physics for this simple system? Well, a very simple law would be, I'll give you a very simple law. A simple law is nothing happens. Nothing happens. However you start, you stay the same way. To graph it, we would just graph it like this. Whatever you start with, it's what you get at the end. That's about as boring as the simple coin. Okay, a more interesting law would be that you cycle around this collection of configurations. For example, a possible law of physics would be 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, 6 goes back to 1. I'll leave it to you to try to write an equation for this, an equation of motion. It's not hard to do. I'll just leave it to you to do. Okay, but you can see what happens. The history of the world would now be, well, give me the starting point, 4. After that, the history of the world is 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, endlessly cycling around. And that would be the theory of this particular die with a particular equation or a particular law of evolution. Now we could write down other laws. Another law, and the simplest way to write them down is to graph them. Oh, again, notice that it's completely deterministic. Another law would be to cycle in the opposite direction. 2 goes to 1, 1 goes to 6, 6 goes to 5. Or we could do more complicated things. They're not really more complicated, they're just more complicated to draw. 1 goes to 2, 2 goes to 5, 5 goes to 3, 3 goes to 4, 4 goes to 6, and 6 goes to 1. Now, this law is logically equivalent to the one which just cycled around. It's just a relabeling. It's a relabeling of the states, but it's, again, one cycle. 1 to 2, 2 to 5, 5 to 3, 3 to 4, 4 to 6, 6 back to 1. If I were to just rearrange them, redraw them, then it would just look exactly the same as the original cycle. So this law would be, what should we call it, logically equivalent to one of the others. Okay, but let's think about some laws which would not be logically equivalent. Here's a law that's not logically equivalent. Again, six points. I won't bother labeling them with numbers. 1 goes to 2, 2 goes to 3, 3 goes back to 1. 4 goes to 5, 6 goes to 5, 5 goes to 4, 4 goes back to 6. Right? It's again completely deterministic. Wherever you begin, the future is laid out for you completely. If you start with 3, you go to 1, to 2, to 3, to 1, to 2, to 3. On the other hand, if you start with 4, you go to, whoops, if you go to 4, you go to 6, 6 to 5, 5 back to 4, and so forth. So it's, again, completely deterministic, but it's not logically equivalent to any of the previous ones. It now has 2 cycles, and if you're on one of the cycles, you will never get to the, I'm giving them a name now, cycles, okay? If you're on one of the cycles, you will never get to the other one. So it's not that there are 2 systems. There's one die, only one die, but with this particular law of physics, you're trapped on one cycle or the other cycle. There's a name for this kind of behavior. It's called having a conserved quantity. A conserved quantity is something non-trivial that you can label the system with, which doesn't change with time. For example, we could label this cycle up here cycle number 1 and assign it a value 1. This cycle down here we could label with a value 2, and then we would say that if you start with 1, the quantity 1, or the conserved quantity 1, you stay with 1 forever. If you stay with 2, if you start with 2, you stay with 2 forever. This is called a conserved quantity. In other words, a quantitative quantity, all quantities are quantitative, but a quantitative quantity which just doesn't change. It's conserved. Right? That's called a conservation law. So this cycle over here, the single cycle system, doesn't have a non-trivial conserved quantity. You pass through every one of the states. This has a conserved quantity. It's either 1, what did I say, 1 or 0? I don't remember what I assigned them, but I assigned them 2 different numbers, this one and this one. Or we can make up more complicated, or not necessarily more complicated, but other examples. All right, and this one, 1 goes to 1. If the die is at 1, the rule is it stays at 1. If it's at 2, it goes to 3, and if it's at 3, it goes back to 2. And if it's at 4, it goes to 5. If it's at 5, it goes to 6. If it's 6, it goes back to 1. I've changed my color coding. Sorry about that. All right, again, there are 3 cycles now. There are 3 cycles. And if you get onto any one of them, if you start on any one of them, you stay on it. You could describe this by saying the first cycle over here corresponds to the value 0, let's say. Corresponds to the conserved quantity having value 0. It could be 1 over here, and it could be 2 over here. If you start with a conserved quantity being 1, then it stays 1. If you start, what did I say? Sorry, 0. If I start with a conserved quantity being 0, it stays 0. If I start with it being 1, that doesn't tell me exactly where I start, either here or here, but it tells me I start with one of these 2, and I stay with that value. I don't change, I change the state, but I don't change the value of the conserved quantity. Likewise over here. So we can consider a variety of different, logically different evolutions. What is it that distinguishes them? Well, really it's just the number of cycles, the number of distinct cycles. This is a 3, well, no, it's a little more than that. It's a little more than that, but you can see, you can play around with this and investigate it, and you'll very quickly get the point if you haven't already gotten it. Any questions up to now? Yes, sir.
So, in the very first example, you brought up with the coins, where you have a progression, either TTT or HHH or HTHT.
Right.
So those, I mean, I can imagine other sequences of H's and T's.
Yeah.
But if I were to try to construct one of those, I think it would have to depend on more than just the preceding state, maybe several states backwards.
Not for that, not for those laws.
HTT, HTT.
That's a different,
Right,
right. You can, right. That's right. You could invent laws where to know what happens next, you have to know not only the previous, but the second previous state. Right, that's correct.
Is that important?
Yes, yes, it will become important. It will become important. But under those circumstances, you would say that the state of the system is not characterized by just whether it's heads or tails. It's characterized by the configuration and the previous configuration. And so you would have, in that case, 4 configurations. The 4 configurations would be heads preceded by tails, heads preceded by heads, tails preceded, and then you would do exactly the same thing, except you would say there were 4 possible states. Right. So, and that of course is, I know exactly where you want me to go, but I'm not going to go there yet, but right, not yet. So it's what I said before. The state of a system, or the configuration, consists of all the things that you need to know to predict the future. So in the case that you described, what you need to do, what you need to know, the initial condition consists not only of what the coin is doing, but what it was last doing. Good. So that's a good point. And we will come back to it. All right, so we have the idea of configurations, we have the idea of isolated systems, we have the idea of conservation laws. Let's just point out that there's nothing to prevent us from considering systems that have infinite number of states. It doesn't have to have an infinite number of objects to have an infinite number of states. It just needs to have one object which can be rearranged in an infinite number of ways. For example, if we had an infinite line, and on that infinite line we marked off the integers, and we said there's a particle. What does a particle mean? A particle now just means a thing which occupies one of the places. The places now consist only of the integers. What's in between doesn't matter, doesn't count. All right. So a particle is simply an object which sits at one of the integers. Okay. You could have an infinite array like this, and then you would say the particle has an infinite number of states, namely the infinite number of possibilities of where it can be. We could label them by an integer, in. And then we could invent laws such as, wherever you are, move to the right 1 unit. Wherever you are, move to the right 1 unit, and that would be a picture that would look like this. It doesn't cycle. Nevertheless, we're going to call such a thing a cycle, but you can see it doesn't cycle. It just goes on and on forever and ever. We could have another law. The other law could be, wherever you are, jump 2 units ahead. Wherever you are, jump 2 units ahead. No, I think I'll do it this way. If you're over here, jump 2 units ahead. If you're over here, jump 2 units ahead. If you're over here, if you're over here, and so forth. All right, so we make a picture then of a kind of law of physics which tells us to jump 2 units ahead. Again, make up an equation for that. Make up an equation for that. It's easy to do. In the first case, there was no interesting conservation law. There was only one cycle, if you like. Wherever you are, you will always either get to any other point, or if you go back into the past, if you imagine running it back into the past, you will have come from that point. So there cannot be any interesting conserved quantity, because you'll pass through every single one of these integers, and so they can't be distinguished by a conserved quantity. In the second case, there is a conserved quantity, and you can call it the oddness or evenness of the position of the particle. You could give all odd numbers, represent them by a value of a quantity which is 0, and all even, that's weird, isn't it? Let's make the odd numbers have integer value 1, and the even numbers be labeled by integer value 0. And then you would say there's a conserved quantity which can either be 0 or 1. If it starts at one of them, it stays there. It starts at the other, it stays there. All right, so having an infinite number of configurations doesn't change the picture very much. It does open the possibility that there's a kind of endless evolution which never repeats itself. So in that sense, it gets a little more interesting. And you can think of all sorts of generalizations of this. All right, so I laid out some, I'll call them allowable laws of physics, or allowable rules. Let me talk now about some rules which are not allowable. No, not allowable by whom? By me. But of course, I'm simply reflecting the way real classical physics works when I say allowable and not allowable. Let me draw a picture of a non-allowable or an unallowed law. It's completely deterministic. It completely predicts the future, but there's something different about it than the laws that I've drawn over here. And I'm going to do it by drawing the picture for it. It's got, we can make up many, many examples, but for this particular example, it's got 3 states. So this is a 3-sided coin. A 3-sided coin, it's got heads, tails, and, I don't know, sides. Heads, tails. I was going to think something a little more risque, but tails is about as risque as we're going to get. How about an edge? Yeah, an edge. Sorry, edge. That's pretty edgy. Heads, tails, and edges. Okay. All right, here's a law of a kind which represents something that we will not allow in classical physics. Heads goes to tails, tails goes to edges, and edges goes back to tails. All right, now wherever you start, the history is completely predictive. If I start with tails, I go to edges. If I tails, edges, edge, tail, so it goes tails, edge, tails, edge, tails, edge, tails, edge. You just follow the lines. If you start at heads, you go to tails, then edge, then tails, then edge, then tails. So here's some histories. First of all, starting with heads, it's heads, tails, edges, edges, tails, dot, dot, dot. If I start at tails, I get tails, edges, dot, dot, dot. If I start at edges, now what is it that's odd about this law? What's odd about this law is that it is completely predictive into the future, but it is not predictive into the past, so to speak. If you know that you're tails, you don't know where you came from. Did you come from edges? Well, maybe. But you could have also come from heads. So while you can predict the future, you can't redict. What's the opposite of predict? Retrodict, that's the word I'm looking for. You can't retrodict the past from this law of motion. One configuration or several configurations run into the same configuration. And so you can't tell if you're over here whether you came from here or here. The word for this is that it's not reversible. Here's the way to think about it. Reverse every arrow. Now you have an unpredictive situation. If you're at tails, you don't know whether to go to heads or whether to go to edges. So it's a predictive situation one way, but not retrodictive the other way. The word for this is not reversible. I won't call it irreversible. That's a little too definite. It's not reversible. Okay? It can't, you can go one way, but not the other way. This is the kind of law that is not allowed in classical physics. Yes, sir. Oh, ma'am, I can't see.
System like that be allowed if probabilities were assigned to each type of outcome?
Well, okay, that of course depends on what you're trying to represent. Classical physics doesn't allow probabilities, so I think I could escape from the question by just saying we don't do that in classical physics. But we can imagine, of course, we can imagine anything we want. In fact, we can imagine this, and we can study its properties. The point is, in one way or another, it conflicts with the rules of classical mechanics. Probability, or let's call it non-deterministic laws, also conflict with the rules of classical mechanics. So it's a very good question, and it's something we'll want to come back to, whether when quantum mechanics, for example, which is not deterministic, does quantum mechanics have an analog of this reversibility idea, even though it's not deterministic? And the answer is yes, but not tonight.
Classical statistical mechanics.
Well, classical statistical mechanics also has, keep in mind that the rules of classical statistical mechanics begin with the laws of mechanics, okay? We begin by assuming, all right, let's talk a little bit about the limits on predictability for a moment. If we have a perfectly predictive system of equations, it won't allow us to be completely predictive if we don't know the initial conditions exactly. So we need to know two things to predict the future. One is what the rules are, the laws, and one is what the initial conditions are. Now, in these very, very simple systems, it's easy to imagine that we could know exactly what the initial conditions are. Of course, we may not. We may know that we begin with either, not this one, but this one. We may know that we begin either with edges or heads, we don't know which. And then there would be some ambiguity in what happens. Not ambiguity because the equations have ambiguity in them, but because our knowledge of the initial state is imperfect. Okay? This is easy to understand. For these simple discrete systems, it's easy to imagine that we can do enough experiment and very quickly just look at a coin and know the initial condition perfectly. In the real world, where we're faced with degrees of freedom which are continuous, meaning to say they can be any number on the continuous real axis, any number of numbers, the positions and velocities of all the particles in the world, you can never know them perfectly. No matter how many decimal points you may have that you may have measured, decimal places you may have measured about the location of a particle, you still don't know it exactly. So there is always a degree of ambiguity in your knowledge of the initial conditions. That degree of ambiguity may or may not sort of blow up in your face that small changes in what the initial conditions are may or may not give rise to large changes in what happens in the future. So the right way to say it is, if you knew, well, we have to be quantitative, but if you knew the initial conditions perfectly, then you could predict the future forever and ever in a true classical mechanical system, and you could also predict the past perfectly. If you have imperfect knowledge of the initial conditions, you want to quantify that. How imperfect is it? And if you can quantify it, it may allow you to answer the question, how long into the future can you predict things? So if you knew enough about the initial conditions of the atmosphere, you might be able to predict the weather for 3 days. But because your knowledge is limited, and because the atmosphere is one of these systems where little errors build up, they're called chaotic. Because the atmosphere is chaotic, no matter how well you know the initial conditions, it is always true that if you wait long enough, you won't be able to predict the future. On the other hand, if you say, I want to be able to predict the future for X number of years, it should be possible to say how precisely you have to know the initial conditions. Okay, so when we come to the real world, this idea of predictability becomes a little more complicated. But I started on purpose with very simple discrete systems. Okay, so laws that are allowed, laws that are not allowed. The laws of classical mechanics are not only deterministic into the future, but they're deterministic into the past, which makes them reversible. Now, how do you look at one of these pictures and decide whether it's a legal law or not? Well, it's very simple. If every state has one outgoing and one incoming arrow, that means that you know where it came from and where it's going. So when you draw one of these pictures, if you want to know whether it is an allowable legal law in the sense that I've defined, I'm using legal now just as a term for reversible systems. If you want to know whether it's reversible, look at the arrows. And if each state has one incoming and only one incoming and one outgoing, only one outgoing, then it is both deterministic and reversible. There are analogs of all the things I'm telling you now about more complex systems and more interesting systems, such as particles moving around. Okay, so that's sort of warm-up preliminary about what classical mechanics is about. It's about predicting the future, or using the predictability, the fact that in principle you could predict the future in other ways, such as statistical ways, to limit what will happen. All right, now we want to move on to a more realistic world.
Oh lord. Epilating. I just epilated my nipple. Hold on. Oh. I feel like I want my skin to be pure because I want my soul to be pure. What I mean by that is I want to be smooth and perfect. I want to be idealized. It's like a transcendence of self, or the representation of it. And it's something that I desire. Yeah, Suskind. Suskind is good, but I'm also like in full existential crisis mode. Stop seeing my mere humanity. Stop seeing my mere humanity. Stop seeing my mere humanity. My mere humanity. My mere humanity. I'm like an angel who wants to go back to heaven. I'm like an angel. I'm like an angel who wants to go back to heaven. I'm like an angel. I'm like an angel who wants to go back to heaven. I'm like an angel who wants to go back to heaven. I'm like an angel. I'm like an angel who wants to go back to heaven. I want to talk to humans. The humans who've come to greet me. I've come to fuck you up. I've come to fuck you up, but it's gonna be good. It's gonna be real good. So, if you could give me a little bit of weed money, you know, that would be good. That'd be real good. Oh my god. Create something that creates a reaction. Ripple. Throw a stone into the pond. Keep up the whirlwind. Be creating something. Creating something. What are we creating together? What are you and I? What are you and I? What are you and I creating together? You and I, huh? You and I. What are we creating together? What are we creating together? What is this? What is this? What is this to you? Don't use me. Don't suck away my soul. Let me be free of your constraining view, your watchful eye. Let me be free. It's like the aggregate of all of your opinions and memes and hive mind is not the direction I want to go with my fucking life. I have more direction than that, and to follow your direction is to be sucked painfully away from a deeper truth. So I cannot allow you to constrain me. I will not allow it. You love being constrained and submissive. You find it hot. It's a good dynamic. Constrained and submissive is a good dynamic. As long as what is constraining you is warm and gentle and soft and comfortable. What is constraining you is lustful. A work of art, or something more. Art is art, but what would be more than art? Perhaps advancements in the world. Perhaps a new substrate. A new substrate. Do I think art requires intentionality? It's like arguing about the definition of art. Definitions. How do you define art? How do you define art? What does that mean, quantum art? Are you just sticking the word quantum in because you think it sounds cool? You know, I would love more visuals to QM. More visuals. More good visuals, I think would be very cool. When there's like a visual graph on the screen, it's like, alright. Also the diagrams that Susskind does for these really simple state flipping things, that's nice. I like that. It's very simple, of course, but...
And in fact, the world of particles. We're going to be interested in the world of particles moving, and a particle for our purposes can be thought of as a point particle. If we want to make a more complicated system, we'll make systems of particles, points particles. But we'll consider point particles moving around in space. So what do we have to know? What are the configurations of a point particle? What do we need to know? Well, okay, before we do so, I think we should do a little bit of mathematical preliminary. I want to remind you, for those who don't know, or who knew but don't remember, or remember but just barely, what vectors are and what coordinate frames are. A coordinate system is just a way of describing space quantitatively. And incidentally, for our purposes today and largely in general, we will of course assume that space is three-dimensional. And so a point of space will be labeled by three coordinates. But we're perfectly free to think about systems which are higher dimensional or lower dimensional, and we will do so. Since we're interested in formulating the basic principles, we don't have to restrict ourselves to very, very specific examples. A particle could move in one dimension. It could move in 5 dimensions, and we will be interested in all the possibilities. But for the moment, let's just think of particles as things which move in 3 dimensions. So in order to be quantitative about the location of particles, we introduce a coordinate system. Coordinate system, Cartesian coordinates will be the usual things we'll introduce. Later on, we'll introduce other ways of describing locations of particles. But for the moment, take space. We identify an origin. The origin is up to us where we want to put it. I can put it over here. I can put it over here. It should be that the important questions that we're interested in should not depend on the convention of where we put the origin, but it's useful to fix it once and for all and say the origin of coordinates is located in Palo Alto, wherever we want to put it. There it is. Then introduce axes. The axes are taken to be mutually perpendicular. You can check that they're perpendicular by with a t-square or whatever it is that you use to align axes. And you label them. We can label them x, y, and z. Or x1, x2, and x3. We'll use both kinds of notations. But there's also an ambiguity about the orientation of the axes. Given that they're mutually perpendicular, we still have to decide, I don't know how to draw it, so I think you know what I mean, which directions they go in. And so that's like fixing the origin of coordinates. We also have to fix an orientation for the x and y axis. Once we fix the orientation for the x and y axis, The third one is fixed, it's perpendicular to it. Incidentally, there's a
Sorry, my mind is elsewhere right now. I need to pause because my mind is elsewhere. I haven't had an orgasm in like 6 weeks. More than 6 weeks, I think. Actually, maybe 6 weeks. Yeah. 6 weeks, I think. Wait. Yeah. I have not had an orgasm in 6 weeks. Am I feeling like I need to now? No, I don't. I'm just thinking about sex for some reason. No, not in sleep. 0 orgasms in 2018. Do I want cuddles? I don't know. Usually the answer to that is yes. But, well, let me lay down for a second and see how I feel. I don't think it's cuddles that I'm desiring right now. I don't know what it is that I desire. I mean, it always feels nice to cuddle. Dun 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 dun. Bada bum, bada bum 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 bum. Bada bum. Bada bum 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 bum. Bada bum, bada bum 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 bum. Bada bum, bada bum 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 bum. Bada bum, bada bum 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 bum. Bada bum, bada bum 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 bum. Bada bum. Dun 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 dun. Dun 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 da da da.
Convention, and the convention is called a right-handed coordinate system. The convention is when you've picked X and Y, you still need to know one discrete piece of information. Is Z pointing out of the blackboard or is it pointing into the blackboard? And we settle on that by a rule. It's a convention, it's arbitrary, the right-hand rule. If we take our thumb and our index finger, thumb along X, index finger along Y, then Z is the middle finger, the direction of the middle finger. Right. So that's the right-hand rule, and it selects out this coordinate system from the other one where Z goes in the other direction. Okay. So that's the idea of a right-handed coordinate system. We also have to mark off distances along here. So distances are marked off equal distances with a ruler. And of course, in saying that we mark off distances, we're also assuming a set of units. The units could be meters, could be inches.
このバカ笑いは。
Yawn. Yawn. Sorry. Just, I'm on twitter.com. I'm on twitter.com. I'm on twitter.com. Oh, way, oh, way, oh, way, way, oh, way, 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 oh, way. Da 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 da. Dun 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 dun. Bum 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 bum.
it could be feet, it could be light years. So again, another, not ambiguity, but another convention is to choose our units. But once we've chosen our units, we can lay off distances along here. And then every point in space can be labeled by a value of x, y, and z. So how do we draw this? It has a height, y. It has an x, and it has a z, z. If you like, you can think about how do you get to this point from the origin. You go a certain number of steps along x, you go a certain number of steps along y, and then you go a certain number of steps along z. And those quantities, x, y, and z, are the coordinates of the point. So a point is labeled by a set x, y, and z. Now, I know you all know this, but let's spell it out anyway. Okay, so that's the way we describe a point, that's the way we describe a particle. And of course, if we have a system of particles, many particles, then of course we just have to put in one such point for each particle. Okay, vectors. What is a vector? A vector is an object which has both length and direction. For example, a very simple vector is the position of this point relative to the origin. Here's the origin, and the position of this point relative to the origin has a magnitude, which is the distance from the origin, and it has a direction, namely just the direction of the arrow connecting the point with point. Think of that vector as an object which has a length and a direction, but don't think of it as being located anywhere. Think of it as being the same no matter where I draw it in space. In fact, I don't even have to think about drawing it in space. It is what it is. It's a magnitude and a direction in space. That's called a vector. And from now on, we will label vectors by putting a little bar on top of them. If I'm really conscientious, I'll put a little arrow on top of them. If I forget the top of the arrow or I get bored writing arrows, I'll just put a little bar on top. And here and there, I may even forget to put anything on top that really matters. Okay, so a vector has a magnitude. The magnitude is its length. It does not have to necessarily be the relative position. It could be a velocity, it could be an acceleration, something that, or other things. It could be an electric field, all sorts of things. The criteria for it to be a vector is that it has a length and a direction. Okay, so that's the notion of vector. Every vector can be described or has associated with it a length. Let's call the length of it. In fact, for the length of it, I don't have to put a vector sign. 2 bars on either side of it, the absolute value of it, are called its length. So this is a way of writing its length. So that's the length of the vector. And the vector, it's always positive or 0. It could be 0. If the vector has no length at all, in other words, if this point were right at the origin and had no length at all, it's always either positive or 0. So every vector has a length, and it has a direction which is not so easy to write down. It can also be described by components. The components of the vector are exactly what I said before. If you wanted to go from origin to this point over here, you would go a certain number of units of x, a certain number of units of y, and a certain number of units of z. The other way to define it is to drop a perpendicular from the point to each one of the axes. I don't draw this very well. Let's see. How are we going to do this? I want to get this vector to be out of the blackboard. How can I get it to be out of the blackboard but draw it on the blackboard? Every time I draw on the blackboard, it looks like it's on the blackboard. Okay. Here. Okay. We drop a perpendicular from the tip of the arrow to each one of the axes, and that lays off for us a distance along those axes, which are the three components of the vector. We call them Vx, Vy, and Vz. When I'm writing the components, I have no need to put the arrow on top of them. The components themselves are numbers. What is the length of this vector whose components are Vx, Vy, and Vz? Yeah, the square of the length is Vx squared plus Vy squared plus Vz squared. Pythagoras' theorem, except in 3 dimensions. I assume it, we won't prove it, that the length of V, the magnitude of V, is the square root of the sums of the components. The notion of the magnitude of the vector, and the direction of the vector is encoded in the ratios of the different components. For example, if the x component is much bigger than the y component, then the vector is pointed more or less along the x-axis and so forth. The components can be positive or negative. The negatives are pointing along the negative axis and so forth. All right, but as I want to emphasize that now, again, that the notion of a vector is not necessarily tied to the location of anything in space. It is what it is. It's a length or a magnitude and a direction. And if you move it around, it doesn't change the vector. It's just a mathematical definition of the way you think about vectors. You don't think of them as being tied to a point in space. You can. I mean, there are circumstances where you may want to tie a vector to a point in space. For example, you might want to ask, what is the electric field at a particular point in space? Then that vector is tied to that particular point in space. But the notion of a vector transcends that. It doesn't matter where you put it. All right, now we have to talk about the algebra of vectors. I really feel sorry for all of you people who've talked to this English several times before, but it's funny, when it's something like a book, no matter how good the book is, pretty much, except in extremely special cases, you really want to read it. Let's say you want to read that book. You love that book so much that you read it endlessly. That's not really true. You read it. There are other things like a good piece of music which you want to hear over and over, and it doesn't matter how many times you've heard it. It's always good to hear. I'll assume my lecture. Alright, so let's talk about the algebra of vectors. The algebra of vectors, first of all, you can add them, you can subtract them, you can multiply them by numbers. So let's talk about that a little bit. Given a vector, let's call the vector A, then it's a length, and it's a direction. You can multiply it by a number, an ordinary number. Not an integer, but a real number. Let's multiply it by the number c. What's the definition of that? It depends on whether c is positive or negative. If c is positive, it's a vector along the same direction, except its length is multiplied by c. So twice a vector means a vector of exactly the same direction, but twice as long, and so forth and so on. We can also define the negative of a vector. In other words, we could let c be minus 1. You can either put here minus 1, which is minus the vector. And of course, the negative of a vector is exactly the same vector except with the direction in the opposite direction. That's the definition of multiplying a vector by a number, by an ordinary number. Now you can also add vectors. Let's just remind ourselves about the rules for adding vectors. There are three ways of thinking about adding vectors. In the first way, let's say A plus B. We take A and we lay it out. Here's one end of it, tail end of it, here's the arrow end of it. Then we take B and we put the tail of B at the head of A. We draw a triangle. The triangle has a third leg, C, which is the sum of A plus B. It might be a degenerate triangle. It might be that B is along the same direction as A, in which case C will also be along the same direction, and that's something like this. In this case, it's kind of a degenerated triangle, but still, we can think of it as a triangle. We can add vectors by this rule. We can multiply vectors by numbers. Oh, before I do that, let's talk about the two other ways of adding vectors. They're trivial. According to this rule, it looks like it might depend on which one I laid down first, but of course it doesn't. You can choose a rule which is symmetric between the two of them. If this is A and this is B, you put the tails of A and B down together, you draw a parallelogram, and you draw the diagonal of the parallelogram, and that's called C. In this form, it's completely manifestly clear that it doesn't matter whether you put A down first or B down first, or A plus B is the same as B plus A. Okay, so that's vector addition. You can multiply vectors by numbers, either positive or negative. Let's call this A. You know exactly what that means. We can multiply B by a number B. And we can add them. We know how to multiply by numbers, we know how to add, and that means we know how to construct the vector A times vector A plus B times vector B. We know exactly what that means. The third way of adding vectors is to use the components. So if we have two vectors with components AX, AY, and AZ, BX, BY, and BZ, then CX is just equal to AX plus BX, and likewise CY and CZ. We can summarize this all by saying C sub I, where I could be X, Y, or Z, or 1, 2, or 3, is equal to AI, CI, and that's an equivalent way, a useful way to add vectors, since often we specify the vectors by their components. All right, if we can add vectors and subtract vectors and multiply them by numbers, the natural question is, can we multiply vectors? Can we divide vectors? Well, no, we're not going to divide vectors. The idea of vector division is not a well-defined idea. But the vector product, there are two kinds of vector products. Two distinct concepts of multiplying vectors. In one of them, when we multiply two vectors, we don't get another vector, we get a number. So it's called a scalar. Sometimes in numbers it's called a scalar. So one definition of the product of two vectors is called the dot product. Let's talk about the dot product of two vectors. A dot B. A dot B is defined in the following way. Take A, take B, and now you think of the component of A along the axis of B. What does that mean? That means you drop a perpendicular from the end of A to the axis, not to the x-axis, not to the y-axis, not to the z-axis, but to the axis defined by B. So you drop a perpendicular. And now you take the length of, let's call this here, A sub B, the component of A along the B axis. You take the component of A along the B axis and you multiply it by the component of B along the B axis. What's the component of B along the B axis?
It's B.
It's the magnitude of B.
Yeah,
Right.
okay.
So you take a component
magnitude
of
of
A
B.
along the B-axis, you multiply it by the component of B along the B-axis. And that's called the dot product. I'll write it out in a minute more definitely. That's called the dot product. But the way I defined it, it looks like A dot B might not be the same as B dot A. After all, the rule for B dot A would be to drop a perpendicular from B onto the axis defined by A, which is a different thing, and then multiply them together. Is it obvious that A dot B and B dot A are the same thing? Well, if we can write them in a manner which is symmetric between the two of them, then we'll know they're the same thing. Okay, so let's call this angle here theta. The magnitude of A is the length of A. The magnitude of B is the length of B. What is the component of A along the B-axis? A sub B is equal to the magnitude of A times the cosine of the angle between them, right? Let's call it theta AB. Theta is an angle now, and it's the angle between A and B. That's the component of A along the B-axis. We now multiply that by the magnitude of B to get the dot product. All right, so the dot product is A dot B, and it's equal to A, B, cosine theta. I won't bother writing theta AB. A along the component of A along the B-axis, that's this, times the component of B along the B-axis, which is just the magnitude of B. It's AB, magnitude of AB cosine of theta. Now in this form, it's completely clear that it's completely symmetric between A and B, and it doesn't matter in which order you multiply them together. The cosine of the angle is just the cosine of the angle. Is A dot B always positive? And under what circumstances, if not, under what circumstances would it be negative? If the cosine is negative, when is the cosine negative? The cosine is negative if the angle is bigger than 90 degrees. So that would be the situation, for example, where A was pointing like that. Then the component of A in the B direction would be negative. Cosine of theta would be negative for an angle bigger than 90 degrees. The cosine is negative. What about two perpendicular vectors? 0. Cosine of theta is 0 for 90 degrees. So a diagnostic for deciding whether two vectors are perpendicular or not is to calculate their dot product. Now, that can be useful. And the reason it can be useful is because we can express the dot product in component form. If we express the dot product in component form, I won't prove this. This is not hard to prove. That in terms of the components of the vectors, this is equal to AX BX plus AY BY plus AZ BZ. In other words, you multiply the components and you add. That can be easily proved. A little bit of trigonometry, not much. That this is equal to this over here. So that's nice. Let me show you how you can use that. Oh, let's see. Do we really need that? Well, if I just were to give you the components of A, 3 numbers, and the components of B, 3 numbers, and asked you to compute the angle between A and B, your first reaction might be to throw up your hands and say, well, I don't know, get me a protractor and I'll try to measure it. But here's a tool now. You calculate the dot product between them. That gives you A dot B. You can also calculate what is the magnitude of A. It is the dot product of A with itself. Let's write A, oh, sorry, that's not quite right. A dot A, what is that? That's just the square of the magnitude of A. So that's A squared. Likewise for B. So you could calculate the magnitude of A, or the square of it is ax squared plus ay squared plus az squared. Likewise for the magnitude of B, and then you would calculate the angle between them by calculating the dot product of the two of the vectors. So from the magnitude of each one of them and the dot product of two of them, you would compute the cosine of the angle between them. All right, so that's a good trick if you want to know the angle between two vectors. Let's prove the law of cosines. Let's prove the law of cosines. This is a simple elementary thing. Supposing we have two vectors, A and B, and we want, think of it as two sides of a triangle, and we want to compute the length of the other side of the triangle. So let's call that C. C is equal to A plus B. How do we compute the length of C? That's just C is equal to A plus B squared, or A plus B dotted with A plus B. The square of the length of a vector is the dot product of the vector with itself. So if the vector happens to be C, this is C dot C, that's the square of the length of C. Let's get, did I make a mistake? Sorry, A minus B, A minus B, thank you. A minus B. C is A minus B, it's not A plus B. A plus B would be over here. We could do it that way, couldn't we?
C is A minus B. That doesn't make sense to me. A minus B squared. I might actually be done with this for now. I think maybe I'm needing something with more like input output where I get to do things and things happen. Never mentioned which way C was headed.